You've just received the Geotechnical Investigation Report for your new project site. It's filled with graphs, charts, and terms like liquid limit and cohesion. What does it all mean? And how does it dictate whether you need deep piles or a simple shallow footing? The answers lie in the laboratory. The soil beneath our feet is not a uniform material. It's a complex, variable substance whose properties must be quantified before we can trust it with our structures. In this video, we're going inside the geotechnical lab to unravel the most critical soil tests. I'll show you not just how these tests are performed, but how to interpret the results to make smart, safe, and economical design decisions. This knowledge is the bedrock of all successful construction. We begin our journey with a foundational test that classify the soil, telling us exactly what type of material we're dealing with. The first and most basic of these is the sieve analysis and hydrometer test. A sieve analysis is used for the coarse-grained portion of the soil, the gravels and sands. We pass a dried soil sample through a stack of sieves with progressively smaller openings, shaking them for a standard time. The percentage of soil retained on each sieve is weighed, giving us a particle size distribution curve. This curve tells us if the soil is well graded with a good mix of sizes for compaction, or poorly graded, which can be unstable. But what about the fine-grained particles, silts and clays? For that, we use the hydrometer test. This test is based on Stokes' law, which relates the falling velocity of a particle in a fluid to its size. By measuring the density of a soil-water suspension over time with a hydrometer, we can determine the distribution of these tiny, invisible particles. Together, these tests give us the complete grain size distribution, which is the first step in the Unified Soil Classification System, USCS. The next critical classification test, absolutely vital for understanding fine-grained soils, is the Atterberg limits test. This test, developed by Atterberg, identifies the water content at which a soil changes between three critical states: solid, plastic, and liquid. The liquid limit, LL, is the water content at which a soil behaves as a liquid. A small groove in a soil pat will close over a distance of 13 millimeters after 25 blows from a standard cup. The plastic limit, PL, is the water content at which the soil can no longer be rolled into a 3 millimeters thread without crumbling. The difference between these two values is the plasticity index, PI. The PI is a direct measure of the soil's plasticity. A high PI indicates a clayey soil that will expand when wet and shrink when dry, posing a major risk to foundations. A low PI indicates a silty soil. These simple tests are incredibly powerful. They tell us if a soil is a fat clay, CH, a lean clay, cell, a silt, mel, or something else entirely. A pro tip for foundation design: a high plasticity index is a major red flag for potential differential settlement and requires special foundation considerations. Now let's move from classification to the tests that determine how the soil will behave under load, starting with the standard Proctor compaction test. In the field, we compact soil to increase its strength and reduce its settlement. But how do we know what the target is? The Proctor test answers that. In the lab, we take a soil sample at a specific moisture content and compact it in a standardized mold with a standardized hammer in 3 layers. We measure the wet density of the compacted soil. We then break off a piece to determine its exact water content, which allows us to calculate the dry density. We repeat this process with the same soil, but at incrementally higher water contents. When we plot the dry density against the water content, we get a curve that peaks at a point called the maximum dry density, MDD, at an optimum moisture content, OMC. This is our recipe for the densest, strongest possible soil. In the field, we use a nuclear density gauge to check if we've achieved, say, 95% of this maximum dry density. This test is the cornerstone of all earthwork projects, from highway embankments to building pads. The next set of tests are the heavy hitters of geotechnical engineering, the strength tests. The direct shear test is a relatively simple way to determine the shear strength parameters of a soil, its cohesion, C, and its angle of internal friction, phi. Shear strength is what allows a soil to resist sliding along internal surfaces. In this test, a soil sample is placed in a box split into 2 halves. A normal load is applied vertically, and then the top half of the box is pushed horizontally, shearing the sample along the predetermined plane. We measure the shear force required to cause failure. We do this for 3 or 4 samples under different normal loads. By plotting the shear stress at failure against the normal stress for each test, we get a straight line. The intercept of this line is the cohesion, and the slope is the friction angle. This test is great for sandy and gravelly soils, but it has a limitation. The failure plane is forced, which isn't always how soil fails in reality. For a more sophisticated and accurate measure of strength, especially for critical projects or complex loading conditions, we use the Triaxial test. This is the gold standard. Here, a cylindrical soil specimen is enclosed in a rubber membrane and placed inside a pressure chamber. It's subjected to an all-around confining pressure, simulating the pressure from the surrounding soil at a certain depth. Then, an axial load is applied until the sample fails. The key advantage is that the sample is free to fail along its weakest plane, not a predetermined one. There are different types of triaxial tests that simulate different field conditions, like a consolidated drain test for long-term slope stability or an unconsolidated undrained test for the immediate stability of a clay layer after excavation. The results give us a much more reliable and detailed understanding of the soil's strength envelope, which is directly input into software for slope stability analysis and foundation-bearing capacity calculations. Finally, for structures built on soft, saturated clays, the primary concern isn't immediate failure, but long-term, gradual settlement. This is where the consolidation test comes in. Consolidation is the slow, time-dependent process where water is squeezed out of the voids of a saturated clay, causing the soil layer to settle. In this test, the soil specimen is placed in a ring and sandwiched between two porous stones. A vertical load is applied, and the deformation dial gauge is read over time for 24 hours or even longer. This load is then doubled, and the process is repeated. The data from this test allows us to determine the compression index, CC, which tells us how much the soil will compress under a given load increase. More importantly, it gives us the coefficient of consolidation, Sieve, which tells us how fast that settlement will occur. This is crucial for predicting how long it will take for a building to finish settling after it's built. For a large structure on soft clay, this could be decades. Understanding this test prevents surprises and allows engineers to design preloading strategies or deep foundations that bypass the compressible layer altogether. In conclusion, laboratory soil testing transforms soil from a mysterious, variable material into a quantifiable engineering material with known properties. The classification tests tell us what it is, the compaction test tells us how to densify it, the shear test tells us how strong it is, and the consolidation test tells us how it will settle over time. This data is not just for a report that sits on a shelf. It is the direct input for every geotechnical design decision, from the depth of your footing to the slope of your excavation. It is the difference between building on a known foundation and building on a hope. Now I want to hear from you. Which soil test have you found to be the most challenging to interpret or the most surprising in its results? Let me know in the comments below. If this deep dive into the Geotechnical Lab has been valuable, please give this video a like and subscribe for more content that helps you build your expertise from the ground